Okay, so here's a vector field. Vector field that'll be familiar to anybody who's been in a physics class up to this point of the semester. Okay? You know, calculus-based physics class. Just law of universal gravitation, right? Big G, big M, little m over r squared, big M and little m, the mass of a planet, mass of a satellite, typically. I mean, it could be any two masses.
The larger
Okay.
mass and the smaller mass.
I'm sorry?
The larger mass and the smaller mass.
No, can't understand.
The larger mass and the smaller mass.
Yeah, well, it doesn't even have to be lower and upper, but if the masses aren't a whole lot different, one mass isn't a lot smaller than the other, then you have to go about the center of mass between the two of them. And your R vector would be from the center of mass to the point. So that's just an aside. Okay, so this is just, you know, this should be obvious. Unit vector would be this over the square root of x squared plus y squared plus z squared. And the x squared plus y squared plus z squared would be your r squared. And that should be completely obvious, both from this course and from a physics course. Okay. So we have some path that's parameterized in terms of t. Okay? And A and B are 2 points. So it's like, okay, we got a planet here. Here's our mass, big M, and here's our mass, little m, going from A to B somehow. Now, if you want to think in terms of gravitation, you could think of this as being 2 points on an elliptical orbit. Okay? That would be okay. And, well, we'll see what we get. When we integrate this with respect to position, we're going to get the work done by the gravitational force, right? Okay? Still, okay, A is the point x of A, y of A, z of A. Not particularly important for doing the integral, but just to get us oriented to the notation and so forth, and what everything means. It's x of B, y of B, z of B. Make sense? And we've got a path, okay? Now typically in orbital paths we're going to use more natural paths, and this is highly unnatural. But here's our path.
Maybe there are several planets or moons that are affecting its motion.
Be a pretty funky combination to give you that, but maybe, okay? You can work that one out. You give me the configuration and the relative motion of all these things so that you get a path that looks like this. Give you an A for both courses. Okay. But it's got to be really good, publishable. Now, you know, just work it out for arbitrary path. Give me the path, I'll tell you what needs to move where.
I mean, if I were to go about it, I just make a bunch of circles and just go like from here to here, and then I'm going to use this circle instead, and then this circle.
Well, yeah, but you don't have circles, but that's a good thing to start with. You could kind of break this into little circles and do successive approximations, right?
Would you have to find the points of concavity?
The what?
The points of concavity?
Force of concavity?
The points of concavity.
Oh, okay.
On that curve.
You mean point of inflection?
Yeah. Yeah, that.
Well, points of inflection would be useful, and radii of curvature and center of osculating circles, maybe.
Like if I had to do
Okay.
it, I think it'd be the simplest way would be circle here, circle here, and then from here to here have an x equation and from and a y equation as well, and then have a circle here.
Yeah, but tell me what masses you need where and how they need to be moving to make it move along that path.
Fair point.
Okay? And I mean, you can do elliptical, you know, you can do circles and you can do ellipses, which make it even easier to fit the thing, right?
Yeah.
But the details are pretty confounding, okay? Besides, I want continuous functions, not approximations. Although a good set of approximations, I'd give you some credit for that. But I wouldn't waste my time on it right now until you master everything else. Okay? You'll be in better shape to actually figure it out. Anyhow, here it is, right? So we want to know how much work is done. We want to integrate the dot product of the force with the displacement vector. Along the path. And again, if you know physics, you know that's a work integral. If you know calculus, you should know that's a work integral. Okay? Because that's a standard example. We need to start integration. Although it's not done in every calculus class, so maybe not. Okay, but very commonly, it's in the textbook. I don't know of a textbook that doesn't have it, although I've not really.
We did a chapter on work and energy or something.
Yeah. Yeah. Well, now's when you start understanding that chapter. You pass a test over it, probably did well on the test.
It was one of the harder ones.
Doesn't mean you understood it. It means you memorized enough stuff and understood enough stuff in a combination of memorizing formulas and understanding what it means to do okay on the test. Now you're ready to really understand it. And this is where you do, okay?